So, good morning, everyone. Thanks for joining in. And so my name is Francesca Jacopi. I'm professor at the University of Technology, Sydney, and I'm also chair of the New South Wales chapter for IEEE Electron Devices Society. So we are hosting a very, very exciting webinar this morning. So thanks again for joining. And before we start, I would just like to do a short acknowledgement of country. And so we acknowledge that we're hosting this virtual meeting from the lands of the Gadigal people of the Eora Nation. And we also acknowledge the traditional custodians of the various lands on which you all work today and pay our respect to the elders, both past, present, and future. So that I would like to actually introduce our vice chair of the chapter, Professor Bram Hooks from the University of New South Wales, who will actually introduce our celebrated speaker this morning. Bram, it's up to you.
Okay, thank you, Francesca, for a very nice introduction. And it's my honor today to introduce our speaker. So it's Scientia Professor Martin Green. So Martin is a professor at the University of New South Wales here in Sydney, and he's the director of the Australia Centre for Advanced Photovoltaics, which basically involves all the leading groups in Australia working on photovoltaics. His contributions to photovoltaics are too many to sum up, but the most notable one is the invention of the PERC cell, which is currently over 90% of the industrial solar cells. So it shows that research at a university can really have an impact in the real world. This solar cell was actually invented in the early 80s. So that's also an indication how long it can take for good work at a university to be commercialized. So it took more than 30 years, but hopefully we can do it a little bit quicker now. And Martin's team had held the world record for silicon solar cells for over 30 years of the last 40 years. So that's really a remarkable achievement, which was considered like one of the top 10 milestones in solar history. Martin has won numerous awards, so if I would summarize them, that would take the whole 40 minutes, but the most notable ones are the Alternative Nobel Prize, which is the Right Livelihood Award in 2002, the Global Energy Prize in 2018, where he beat Elon Musk, and very recently the 2021 Japanese prize, which is ranked as 0.5 Nobel Prize. So without further ado, I give the floor to Martin to present his talk.
Well, hello everyone, and thank you, Bram and Francesca. As Bram mentioned, I'm Martin Green from UNSW Sydney, and down the bottom there is a photo of the iconic Sydney Opera House, and in the centre is our lab, solar powered of course, and on the right is our solar industrial research facility where we do technology transfer to industry. And as Bram mentioned, we've had some impact on the industry, and that facility has been very effective. So what I'd like to do today is just talk about the recent evolution of solar cell technology and where I think it's heading in the future. So I've got 5 parts to the talk, and the first part is just introductory material. Firstly, what is a solar cell? So, most solar cells now, 95% of them are made from silicon, and this just shows a cross section. So the light, when it's absorbed by a semiconductor or a metal, it excites an electron from lower energy levels to higher ones. But the thing about a semiconductor is that the excited electron leaves a vacancy behind in the state that it was excited from. So both the excited electron and that vacancy move towards each other in energy, but with a semiconductor you sort of have a safety net formed by the band gap. So the relaxation back to its original energy is sort of halted temporarily by the band gap, because it's a large energy jump required, and that slows down the relaxation process, finding a process that can dissipate that energy effectively. So you have a bit of time to work with. And if you just had a piece of silicon sitting there with nothing else, those carriers would eventually relax back and you'd be where you started from. But with a solar cell, you design an electronic asymmetry into the device structure, and that normally takes the form of a PN junction, as is shown in this diagram. The two different light blue and greenish color are the two different regions doped differently. The N-type region, which is light blue in this diagram, it's very easy for electrons to move through that material, because N-type means negative type, which means there's plenty of electrons. And the P-type or positive type has plenty of holes. So it's easy for the holes to move through that material. So that asymmetry in properties means that these photo-excited carriers, the two components of it, the electron and the hole, tend to move off in different directions due to that asymmetry. So if you make a contact to those two regions, you'll tend to get the electrons flowing through the leads to that, flowing from that contact, and any load that you connect between the contacts, electrons will flow through them, complete the loop and link up with a hole on the other side, and then you're back to where you started. So, basically a very simple microelectronic device. The most common form you'll see the solar cells in is in a solar module, shown on the left there, but that's basically a way of protecting the cells from mechanical damage, as well as isolating the community from the electrical potentials that can be quite high in some of these systems. Most systems are now operating up to 1500 volts, so something you don't want stray fingers getting in contact with. So basically you have a glass cover sheet. Your glass is a very cheap, strong, transparent material, and you laminate the connection of silicon cells between that glass sheet and a polymeric back sheet in general. So those, so you have a glass top sheet, and then you have a frame glass, and then these encapsulant layers serve both as an adhesive, bonding the whole module together, as well as a soft layer that allows for differential expansion between the cells and the glass and the back sheet and so on. So it absorbs some of the thermal stresses that you get in the module. So the most exciting thing about modules, about solar over recent times, is the dramatic reduction in costs. So this graph here just shows the average selling price in US dollars per watt. That's how these modules are generally rated. The ones on the right would be about 300 watt rating. So in 2008, second quarter, they were selling, this is wholesale selling price, at $4 a watt, over $4 a watt. So a module like that would cost over $1,000. But over the next 12 years, we've seen this dramatic reduction. So about this time last year, they were selling for 17 cents a watt. So that's 24 times cheaper. So a module like that of 350 watts would cost $50-something. So, a dramatic change from $1,000 to $50-odd. And that's had a big impact on the way you can use the technology. So, quite some dramatic things happening to the left of the previous graph, and then more stable conditions past 2012, the shaded region. And this just shows that shaded region, the data there, on a logarithmic plot. So on this semi-logarithmic plot, the blue curve there, approximately can be fitted by a straight line. So that's what that is a sign of, is exponential decrease in costs. And if you plot the most recent region of that cost reduction, fit a straight line to it, you get something like 20% a year cost reduction compounded. So that's a situation we're in. Even though the previous curves, it looks like things are flattening out a bit, they're not really. The costs are still going down very rapidly. And that's being seen, this is just the cost of the modules themselves, but when you install them in systems in the field, you have to look at the price of the electricity that you can generate from a system like that. And one way of doing that is to look at agreements that have been made for the supply of electricity. So a lot of cities and countries contract for electricity supply through power purchase agreements that are entered into generally after an auction process. But the lower curve, the lower red curve, just sort of plots the prices that we've seen bid companies have signed up to contract to supply electricity at these prices, generally for 15 or 20 years. But I've just compiled there the lowest PPA bids over the last 7 years or so. So you can see that they're falling dramatically, like the costs of the modules themselves. So something like $80 a megawatt hour 7 years ago, and then very rapid reduction around 2016, getting down to $20 a megawatt hour. And then very recently, we've had a bid of $10 a megawatt hour, which if you convert it to the normal household unit of a kilowatt hour, you sort of divide by 10 and you get 1 cent a kilowatt hour as the equivalent amount. So here in Sydney, I'm paying something like 40 cents a kilowatt hour, during the time the sun is at the peak. So 1 cent is really very cheap, and much cheaper than any other form of electricity, as recognised by the International Energy Agency last year. They haven't traditionally been very keen on photovoltaics, more pushing the traditional fossil and nuclear energy generators. But last year they conceded that solar is now the cheapest source of electricity in most countries and now offers some of the lowest cost electricity ever seen. But you can see from those graphs that are there in the background, the costs are still coming down. So what are you going to say about solar in the future? And one of my colleagues has described it as a future of insanely cheap electricity. And that's what we're heading to. So solar modules, within a few years will be something like 10 cents a watt rather than the present 20 cent a watt sort of benchmark. And electricity supply, this power purchase bid of 1 cent a kilowatt hour, will become quite routine rather than just being a sort of a landmark bid. So very low electricity prices. So these large low prices are causing a rapid expansion of the market. So this just shows a graph from Bloomberg just showing how the annual market for photovoltaics has grown, over the last 10 years or so, and some projections into the future. So growth is expected to continue. If you plot that same type of data on a semi-logarithmic plot, you again get regions that can be fitted by straight lines, showing again exponential growth. So the interesting thing about this graph is if you project that growth into the future, you see that last year we had about 140 gigawatts a year of photovoltaics installed, equivalent of about 140 large coal-fired power stations, for example. But if you project the sort of growth that's shown on that graph there into the future, you'll see that sometime over the next decade, we're likely to hit 1 terawatt a year. And in fact, the company shown there, PB Tech, has projected that we'll get very close to that around 2030. But traditionally, projections about photovoltaics have been conservative. It's easier to explain a pessimistic forecast than an overly optimistic one. So these companies are, by their very nature, tend to be conservative in their projections. So sometime before 2030, I think we'll hit that terawatt level. And why is that important? I guess we have to urgently cut back on our CO2 emissions if we're going to keep global temperature rise to anything sensible. And this graph here it's an old one, but a good one, but it dates from 2015. And it shows the black curve at the top, the global carbon dioxide emissions up to 2014, and then a sort of projection of the type of cutback that you'd need to limit global temperature rise to 2 degrees centigrade. And the thing I like about this is it shows the problem that we're facing. And when I first saw this, if you remember back the previous slide, solar was quite expensive, so you didn't really have an option for replacing traditional electricity sources without going to more expensive renewable supply. But since then, those price reductions have changed the situation. So the problem that this slide demonstrates is, despite the best efforts of the 4 biggest emitters shown there at the bottom, they're likely to use up the whole budget for a 2 degrees centigrade rise sometime at the end of this decade. So I was a bit despondent when I first saw this graph and recognised the implications. But with solar likely to hit 1 terawatt a year in production over the period, we have some way of addressing this issue that wasn't available just a few years back when solar was still quite expensive. So if you look at the impact of 1 terawatt a year, that's shown by the little arrows to the right there. So if you're displacing coal from electricity generation or oil from transport, that's the type of impact that you can have on CO2 emissions. So if you can store 1 terawatt a year, year after year, you're going to get on the right kind of trajectory for that 2 degrees centigrade rise. So that recent quite dramatic reduction in the cost of photovoltaics has been very timely, in that it may arrive in time to limit temperature rise to something reasonable, rather than you're going way beyond 2 degrees, which would likely be the outcome otherwise. So that's part one of the talk, just general overview of the issues related to solar. But next one, I'd just like to talk about how solar got so cheap. So what triggered that massive cost reduction? So this is just a history of solar PV costs and prices. The authors of the paper shown there at the bottom just compiled all the data they could find of cost and prices reported at different points in time. And the costs are shown in orange and the prices in blue. So there's not often a big difference because it's been a very low margin industry and costs and prices have been very similar. But you can see, if you, this again is a semi-logarithmic plot, but you can see it can be fitted for a massive 30 odd years by a straight line. And again, that shows exponential decreases in the price. So about 7% a year decrease for 3 decades is shown there. But more recently, we've got into this accelerated mode. Like I showed in the previous graph, we were up to sort of 20% type cost reductions per year. So clearly something quite dramatic happened just around 2005 that caused this change in this slope. So acceleration of the exponential decrease in solar costs and prices. And the person there shown circled, he's the one to blame. That's Dr. Zhengrong Shi, who was my 12th PhD student here at UNSW. And he was obsessed with the idea of setting up PV manufacturing in China at the turn of this century. So that might sound like something pretty simple when you consider what the major role China plays in the industry these days, but back then it was quite a bold ambition, in that China had none of the infrastructure required for manufacturing cells or solar modules. In fact, Zhengrong in his early days had to import the glass for his solar modules here from Sydney here. So there just wasn't any suppliers of solar glass in China back then, which sounds quite amazing now when solar glass supply is dominated by China worldwide now. But this was the first factory Zhengrong set up, got it going in 2002 with help from other members of UNSW, some that left the uni to join him, others just did what they could. I'm doing some of the heavy lifting here, helping to cut the ribbon at the opening ceremony for this facility. But that was extremely successful. So he was able to market his product internationally, and on the profits he was able to expand his capacity, so much so that he caught the attention of some US investment banks, mainly Morgan Stanley and Goldman Sachs, and they encouraged him to do a management buyout of his original Chinese investors that had kicked in $6 million US to get him started. But they provided the funds that he could buy out those original investors, and instead his backers became these more internationally well-known companies like Goldman Sachs. And the original investors, their original 6 million multiplied to 80 million, so they were quite pleased with the arrangements as well. So Zhengrong became the first Chinese-based company to float on the New York Stock Exchange in 2005. This is shown as the day of the listing, and it turned out this was the biggest technology float of 2005. There was a high level of interest in Chinese stocks in the US at the time. So Zhengrong made 400 million from this listing, and Goldman Sachs, one of his backers, made 200 million, the investment bank. So that had an immediate impact in that it had US investment banks looking for other Chinese companies involved in photovoltaics that they could repeat the success of Zhengrong's listing, and it had Chinese companies involved in PV looking for US investment banks to follow in Zhengrong's coattails. So the next two to list took about a year to get organised, but they were Trina and Canadian Solar. So they're two of the big manufacturers these days, but back then they were just doing simply module assembly. So they weren't nearly as sophisticated as the work Zhengrong was doing, but they benefited from his pioneering work and were successful, and that financed them into manufacturing and allowed them to expand to the size they are now. The next three companies were involved in cell processing, and they involved people from our group or trained by our group in those listings. So we're very heavily involved in that transition. So that caused that dramatic cost reduction after 2005 that I mentioned before. And by 2012, as I mentioned, things had settled down and into a more stable, shown on this graph, 12% per year reduction. Then around 2016, there's a clear break point. At least I think this graph shows a clear break point. And I think the issue there was the introduction of new technology. So the red curve starts occurring. And that's a new technology based on the PERC solar cell, which is a solar cell developed by my group at the University of New South Wales. So the cell structure shown at the bottom there, a little bit more complex than the cell structure I showed earlier on, but addressing some of the issues required to maximize the output from the solar module. But that was a new technology introduced on the market about 2016, and the costs of making those cells was reducing quite dramatically. So to maintain market share, the established technology, which is the blue line technology, had to reduce prices very dramatically as well to maintain their market share. So that, that explains that break point that you see there, the introduction of new technology. So in photovoltaics, these learning curves are used here, where you plot the log of the price versus the accumulated volume. So this is sort of a demonstration of learning by doing. The more you make of something, the cheaper it becomes. So you can see again that very clear break point around about 10 to the 4th megawatts per year produced, so 10 gigawatts a year of production. So that's when Zhengrong got into production then. So he was responsible for the first diversion that you can see there. And things were starting to slow down a bit. And then the PERC came onto the market and continued that acceleration. So at the moment, we're in a massive 40% learning rate, or we have been since 2006. So that means every time the production doubles, you take 40% off the cost of the photovoltaic product. And if you follow that through, if the production quadruples, you halve the cost of the technology. So this graph sort of suggests that if you can reach 2 by 10 to the 6th megawatts, which is 200 gigawatts, which is 2 terawatts, sorry. I'm reading my caption there, but you should get to this 10 cent-watt figure I mentioned there. So if you assume, based on those previous figures I've shown for Bloomberg, about 200 gigawatt a year, average up to 2006, we should reach that 2 terawatts, by about 2006. So we're going to see further cost reduction. So now I'll talk a little bit more about the technology, part 3. Will the PV costs keep decreasing? And my answer is yes, foreshadow that. This just shows the transformation of the industry that I referred to before. The blue region there shows that blue technology, which is a technology that was developed in the US in the 1970s. And that and the red region corresponds to cells made on polycrystalline wafers that are not used in microelectronics, and the red shows the crystalline wafers that are used in microelectronics. You require good quality for microelectronics, but the quality requirements for photovoltaics were back then not regarded as demanding. But what you can see around 2016, you see these brown and yellow regions appearing, and that is the PERC technology that was developed by our group back in the 1980s. But it started gaining market share. And the other interesting thing that occurred was, rather than the polycrystalline wafers occurring, there was a switch to monocrystalline wafers because the PERC technology was able to extract more of the wafer potential than the previous technology. So that meant you got benefits from going to better quality wafers that were previously inaccessible to you. So by last year, PERC had gained 90% of the market, and this year it's thought it could nudge 95%, at least according to PV Tech, who prepared this graph. I'll just point out this black region here. That's made, all these technologies are made from wafers that are doped to P-type. So traditionally boron has been used, but more recently gallium has been used as a dopant. And the black regions correspond to wafers made, to cells made on N-type wafers, and the N-type doping is generally provided by phosphorus. So I'll refer back to that a bit later on. So that transition from polycrystalline material, which used a sort of casting technique developed specifically for photovoltaics, back to the monocrystalline wafers as used in microelectronics, involved a return to microelectronics type of processing. So the Czochralski crystal growth is the standard way of preparing ingots for microelectronics, also now for photovoltaics once more. But the thing that's happened for photovoltaics is the recharging of the crucible. So these containers that the silicon is melted in prior to the crystal growth have to be very pure, otherwise the impurities from the container work their way into the silicon, and you don't end up with the quality that you desire. And they're quite expensive because they're pure. But by recharging those crucibles during the growth process, you can use the crucible multiple times, so that you save on costs that way. So the photovoltaic industry has gone to the growth of multiple large ingots from the one crucible. So this just shows a slide from Longy. I'm sorry, the printing's a bit small, but it just sort of shows the growth in the size of the ingots that's been grown for photovoltaics. So back about a decade ago, they were 60 kilogram ingots, and now they're growing 4 or 5 ingots, weighing cumulatively well over a ton, being grown from the one crucible. So that's had an enormous impact on the costs. And you can see a big ingot down there in the lower right. So that recharging of the crucible and the multiple growth has been important. The other thing that's happened is photovoltaics has pioneered different cutting approaches from what used to be used in microelectronics, but microelectronics has also moved to this technology now, but using things like piano wire to multiple wires in parallel to cut through the ingot. The cylindrical ingot is squared off as shown there, and then sliced into ingots, many wafers at the same time, by feeding this piano wire through it. And the most recent technology uses diamond impregnated wires to do that cutting, and that's been another reason why the costs of photovoltaics has come down, as demonstrated in this slide here. So again from Longy, but you might be able to see the full details of it, but the red and grey bars are just showing the cost of the ingot growth, and grey for the ingot growth and red for the cost of making the wafers from those ingots. And 2011 is the 100% figure, and you get up to 2019 where you're down to 20% for both of those through those type of improvements that I mentioned before. So the cost of being taken out of some of these standard, reasonably standard microelectronics processes. PERC has also offered new functionalities. So It's cheap to make a cell that responds to light from both sides. You might wonder what the advantage of that is, but as this slide demonstrates, you get quite a lot of light scattered onto the rear of the module. So in a field installation like this, you get somewhere between 5 and 10% boost in output from that bifaciality, just due to stray light getting on the rear. But if you did something like laying white pebbles on the ground, took a bit of care, you could get up to a 20% boost through that bifaciality. And the PERC modules are about 70% as efficient from the rear as they are from the front. And some other technologies that I'll mention are even more efficient from the rear than that. The other thing that's happened is something we pioneered in cells we supplied for solar car racing in the 90s, but we realized that cutting the wafers into half would allow less resistance loss in the cells, and also shingling them would allow you to save wasted spot in the space in the modules. So the industry has moved to that type of technology en masse now. And rather than the square cells that you saw in some of my earlier slides of photovoltaic modules, now going to rectangular cells, which are cells cut from originally square wafers. And then this shingling type approach is being used by some manufacturers, or others are using other approaches that allow similarly compact packing of the cells. So in this slide shown in the center there at the top, in the regions away from where the cells are interconnected, the ribbon interconnect that's soldered onto the cell metallization has a triangular cross section in the upper regions. That's to reflect light from the metal onto the cell so you don't waste it. And then in the region where the interconnection between the two cells occurs, it's flattened right down. So you have a very thin cross section, which helps with stress relief and everything with the interconnections between the two cells and allows them to be more closely spaced. So this is technology that's happened at the same time as PERC was introduced, and largely due to the fact that the PERC allows easy cutting of the cells into subcells. So for a long time, 6-inch square, 156 millimeter square wafers were the standard. From 2012, they were introduced. And then in 2019, someone got adventurous and went to a 166 millimeter cell. And that opened sort of the floodgates once it was realized that you could cut these into half or even thirds. So very quickly went to 182 millimeter, and 210 is now the largest size that's being used commercially, within the photovoltaic industry. So, just giving you an idea of the comparison of size. So you process the wafer that size and then cut it into smaller bits at the end. So this cell in the background slide is designed for cutting into 2, and this one in the slide here, you mightn't be able to see it, but it's designed for cutting into 3. So that's the standard. So if we look at what's happened in terms of wafer sizes, the yellow just shows the sizes being used in microelectronics as the historical record of that. So the 300 millimeter or 12-inch wafer was introduced, early 2000s, and photovoltaics for a long time lagged behind. So much smaller diameter ingots were grown, but more recently we've gone to these 210 square wafers, which are the largest that you can cut from a 300 millimeter wafer. So we've caught up to microelectronics in terms of wafer size, and that's reducing costs. So I'm just wondering whether that's going to push the photovoltaic industry ahead of microelectronics and let's go to even bigger wafer sizes. So this is a slide from around the turn of the century when the microelectronics switched to 300 millimeters. Prior to that, they'd been going to larger wafers every 10 years or so. So the expectation shown in this slide is going to 450 millimeter wafers by 2012, and then by now we'd be at 675 millimeter diameter wafers, which are massive, as you can see there. But the costs of the photolithography required for the nanometer type resolution required in microelectronics haven't scaled with wafer size, so that you don't get the economic benefits in microelectronics by going to these bigger sizes at present. But photovoltaics doesn't use any fine line photolithography, so that it could go to these wafer sizes. So I'm just sort of thinking that perhaps that's a trend we'll see in the not too distant future. Solar getting ahead of microelectronics in terms of the wafer and ingot sizes being pulled. You know, you need to pull tons of ingot to be economic now, so going to a larger wafer diameter would help with that growth of tons of ingot per crucible. So with the bigger wafers come bigger modules, and there's a 6-foot tall guy there just giving you an idea of some of the current sizes. So for a long time, 1.6 square meter modules were the standard, but now most manufacturers have got a module that's over 2 square meters and even over 3 square meters in some cases. And you'll notice the rectangular cells within these modules. So you're up to 8 foot tall, some of these modules. So the main limit at the moment is the weight. So you try to keep under 40 kilograms so that 2 people can reasonably comfortably lift it, as shown in this slide here. This just shows a big installation going into China. You mightn't be able to see the cells, but they're square, so it's not the latest system going in. But this is the way you know, they're normally installed. 2 people unload them from a truck or a package that's dumped on the ground and carry them to the installation point. This looks like these guys have been carrying it quite a way, so you generally try to make it a bit easier for them, but this is a Chinese system and labour's a bit cheaper there than in Australia. And then, you know, they get them to the installation site and another 2 people, you know, bolt them to the frame as shown here. So that's why you keep under 40 kilo, just so those 2 people can comfortably carry it around like that. But a few years ago, Applied Materials, a US company, developed big 6 square meter modules based on amorphous silicon, and they weighed over 100 kilo, so too heavy for 2 people to comfortably carry around. So they developed mechanical installation approaches to be compatible with that technology. And you know, I think that could be what the industry goes to now. You know, seeing there's a sudden surge in module sizes, that may continue going to even bigger and heavier modules and get away from manual handling at all, cutting back on the human labour costs. So, you know, 2 people would probably be adequate, as shown in that slide. So what's the biggest module you're likely to see? Well, most are transported internationally and to the site locally by 40-foot containers. And so that puts a limit on the size that you could comfortably fit into there. So that would be 40 foot by 8 foot would be the biggest module you could fit into a 40-foot container, which would be about 30 square meters. So, you know, we might see modules that are reaching that size. Something about a third of that size, 10 square meters, so you could put 3 of them end on end within a 40-foot container, you know, might be an intermediate stage. Okay, I'll finish up just talking about longer term technology. Within the cell area, there's 4 competing technologies. The graph on the right just shows the history of technology evolution. The red dots show the early work was done in the US, or the white dots you can see at the bottom there. And then the red dots are when our group got involved. And as Bram mentioned, we've held the record. We held the record for silicon cell efficiency for 30 odd years, shown by that red region there. And then more recently, companies have got involved with serious research into cell development, and they now hold the record for cell efficiency. Panasonic in Japan with 26.7% efficiency. We got to 25 with the PERC technology back a decade or more ago. But these are the 4 competing technologies. There's a PERC cell that is shown there. TOPCon, which is another technology that was pioneered in our group back in 1981, but it uses a tunneling type of contact to the rear to get the electronic asymmetry that I mentioned in one of my earlier slides. You can achieve that with tunneling structures rather than with diffused junctions. And so this is a very effective way of getting a very asymmetric contact to the bulk material for the electrons. So it's a very good electron contact, that type of tunneling contact. A heterojunction structure. Amorphous silicon is generally prepared for solar with about 10% hydrogen included, and that changes its electronic properties. So it acts like a wider bandgap semiconductor than the crystalline silicon. So that allows you to use some technology like 3-5 heterojunction type technology to form the front and the rear contact, giving you that electronic asymmetry through these deposited morphosilicon layers. And then the bottom structure is the interdigitated back contact structure, which has both contacts on the rear, which is good because the top contacts tend to shade the top of the cell, so you put them on the rear, you've eliminated that loss mechanism. That's in fact the oldest of those structures, so it was invented or first suggested in 1977, and the others in the 1980s. If we look at production, this is very similar to the slide I showed earlier, just showing the share of different technologies of the production, but showing absolute quantities. This is in megawatts, so divide by 1,000 to get to gigawatts. So you can see the little black region there. So the PERC is the brown region. For 2021, it'll completely dominate manufacturing, and the black region is the sum of the total of the other 3 technologies that are shown there. So quite small, but expected to expand. This is just a recent forecast of how it might expand. So things will be pretty quiet over the next year or 2, but it's thought that there could be then more rapid growth, so gaining market share perhaps by the middle of this decade. These technologies will compete, and as I showed before, competition between technologies tends to accelerate the cost reduction in photovoltaics as the established technology has to stave off the contenders. So that competition should see very aggressive cost reduction. I won't go into the details of this slide, but all it's showing is that at the moment, the cost of the PERC is lower, both in terms of the capital equipment you require and the material requirements are lower in cost. So lower in CapEx and OpEx, so it has a clear advantage, but that's expected to diminish in time. So what might happen after PERC? Stacking cells on top of silicon is a very sensible way to go. So a little diagram on the right demonstrates the concept, and this just shows what the cell might look like, just thin film solar cells deposited onto a standard silicon wafer cell. But if you can stack cells of higher band gap onto a silicon cell, the uppermost cells can absorb the blue photons if they have a high band gap, and for lower energy photons they just look like glass, so those photons pass through the next lowest band gap cell and so on. So you get this automatic filtering of the sunlight where the photons end up in the right cell automatically. So the high energy photons end up in the high band gap cell, which is able to convert them more efficiently than silicon can. So if you look at the limiting efficiency, this graph just shows this. For a single junction cell, silicon has a limiting efficiency of 29. We got to 25% with PERC, and I think we'll see those type of efficiencies in production. The red line just sort of shows what you can do if you had any choice of silicon, just dumped silicon and could use any other semiconductor idealized properties. So silicon is a very good choice, as these slides show. But with 2 cells stacked onto silicon, if you can get the same percentage of the available performance, you'd be up over 40% efficiency. So a big jump in efficiency if you can perfect this technology. The main challenge is finding materials that you can stack onto silicon that have the 4 desirable properties that silicon possesses: abundance, non-toxicity, stability, and an efficiency over 20%. So I've listed several compounds that are being looked at there, but none of them tick the whole 4 boxes. So there's still important work to be done in the research area in finding technology that you can stack onto silicon. So stacking one cell onto silicon definitely makes sense. You get a big boost in performance. The second cell you stack onto silicon comes at very little extra cost. But each time you stack a cell onto silicon, you share the available photons between all the cells. So with a 3-cell stack, silicon is only seeing 1/3 of its normal photon count. So its power contribution to the stack goes down to 1/3 of what it would be. So you go to a 4-cell stack, the silicon contribution would be going down to 1/4 of what it normally is, and you just wonder if the silicon was really required. By then, the materials that were stacking onto silicon would be well validated. So my prognosis is that the first 4-cell stack will be an all thin film tandem using whatever technology that ticks all those 4 boxes that I mentioned previously. So that brings me to the end of the talk. So some of the points I wanted to make. Silicon photovoltaics has become very cheap, but it's going to become a lot cheaper. So insanely cheap, as Reme's name mentioned. Competition between new technology accelerates the rate of price reduction. So the fact we have technology sitting in the background that are going to compete against PERC is very important in keeping the pressure on PERC to continue reducing costs. Are we going to see US 10 cents a watt, 22 to 23% efficient solar modules within the next few years, and 1 cent per kilowatt hour electricity prices from solar module? And solar is destined to play a major role in mitigating global warming. So thanks very much for your attention. Be happy to take questions.
Well, thank you, Martin, for your excellent talk. And we'll go to questions now. The first question is from Francesca.
Thanks, Bram. Martin, thanks a lot for your talk. It's not only it's very inspiring and very optimistic as well. So it really the future looks really bright in that sense, literally. And one thing I did want to so it was really also interesting to see how the wafer size is increasing in this. I'm more from the microelectronic prospect, so using the round wafers that are now 300 millimeters at maximum. We stopped to, as far as I know, working on the 450. And so it's really interesting to see how solar now is potentially going further than that, and might be driving the other way around. Might be driving future progress also for microelectronics. But regardless of that, I wanted to ask you something else. What do you think regarding, well, in the equation of using efficiently solar? Of course, there's also the paradigm of the storage. How do you think that part plays a role in the uptake, in a major uptake of solar worldwide? Do you think it's really still a bottleneck, or do you think that actually that problem will be solved and it's not going to be a big issue going forward?
Yes, I think the costs of the lithium-ion batteries are coming down just about as quick as that of silicon photovoltaic modules, so they're in sync at the moment. So yeah, we're seeing very dramatic reductions in the costs, and as you'd be aware, in Australia there's large numbers of battery storage systems going in to help with the integration of photovoltaics into our electricity supply network. So I think that trend will continue and perhaps accelerate as batteries become cheaper and cheaper. But you know, there's some battery installations, like one in Victoria in Australia, going in later this year, that's 300 gigawatts, you know, so 300 megawatt rating, and you know, about 4 hours of storage. So you know, it's getting to the size of a coal-fired power plant in terms of the electricity it's able to supply to the grid, and you know, for quite a reasonable duration. So I think that in conjunction with solar would be you know, a very good match. And then there's always pumped hydro, which has been the traditional way of storing electricity in the grid, mainly for nuclear power plants. But it is also looks like an economic option. And in Australia, there's been a big interest in off-river pumped hydro storage systems. So there's like dedicated pumped storage systems that you know, look economic in terms of the costs of storing electricity that way. Just much longer lead times than batteries. So thanks for the question.
Okay, so we'll go to the questions from the audience now. And Emma had a question about light-induced degradation for PERC. Could you please explain what is meant by that, and has it been resolved, Martin?
Yes, as the solar cells become better and better, you know, more and more of the intricacies of what's happening within the silicon material under sunlight become obvious. So, you know, you're sort of, when you've got a poor cell design, a lot of what goes on is hidden by the parasitics within the cell. But as the cell performance improves, you get to see more and more of what's happening, and there's some very subtle interactions that happen in silicon amongst the impurities which are there in parts per million or even lower concentrations. So I mentioned the industry used to use boron as a dopant. It used to have a lot of interactions with oxygen and iron elements and light. So that combination created defects that were metastable and so on within the material and could be seen in a drop in module performance or an increase if you got rid of them. But now, as I mentioned, the industry is going to gallium for doping, and part of that reason is to address light-induced degradation. So there have been techniques developed, some at our university for mitigating light-induced degradation in boron-doped wafers, but the industry seems to not be taking any chances and going to gallium-doped wafers to avoid those issues. So with a module from a recognised supplier these days, there shouldn't be any issue with light-induced degradation, although it has been an issue that has occupied a lot of attention over the last decade. So thanks for the question.
Okay, thanks, Martin. Then another question from Hema. You would like to ask what's the current lifespan for PV modules? Is it still 25 years, or are we pushing towards maybe 50 years?
Yes, it's tending to increase. So with these bifacial modules, you need to have a transparent backsheet rather than the intransparent, highly reflective one that's commonly used. You need one that's non-reflective, essentially, and transparent. So, obviously a good candidate for that is glass. You can get transparent polymeric backsheets, but glass is a good candidate. So that helps seal out moisture from the module. And most module suppliers that are supplying glass modules will now give you a 30-year warranty. So there's been a 5-year increase, and some are specifying reduced degradation rates. So the standard offer was for a long time, probably since the turn of the century, has been 25 years warranty with over 80% of performance at the end of those 25 years. But now some manufacturers are offering 30-year life with over 94% of performance at the end of those 30 years. So things are definitely improving as people are investigating possible degradation modes within the modules more thoroughly and taking pains to eliminate them. So I think we'll eventually see 50-year module life. It's not a high priority at the moment because 30 years is long enough for most installations, and when you do levelized cost type of analysis, what happens after 30 years becomes not all that important. So the discounting of future earnings sort of mitigates against that being an active area of research, but just maintaining low annual degradation rates is of strong interest rather than the 50-year life per se. So thanks for the question.
Okay, and the next question is from Lim Garat. He's asking basically about how cheap can silicon get, or commercial modules, because he feels that we've already squeezed out anything we can in terms of cost reduction on the module side and installation side. So is there still room to go below 10 cents, or when will we actually reach this 10 cent?
Yes, 10 cents is definitely achievable. So that's about half of what present module prices are. And when you see those curves that I showed with these exponentially decreasing costs, there's no hint in those of that type of rate of decrease slowing down. And largely through economies of scale, manufacturers are sticking in larger and larger facilities and buying materials and things in larger and larger volumes. So all that is, one big contributor to that reduced cost. The improved efficiencies of the technologies I mentioned is another big contributor. So all that is pushing the cost down. So I can see, like a halving of present module prices from 20 cents a watt to 10 cents a watt. I think we're going to see it in the first half of this coming decade. And, perhaps there's another halving beyond that. I don't think it depends too much on the technology. So, I often read papers that talk about silicon being expensive, and hence we need to do work on some or other exotic material. But the reality is that the glass and the frame and the transport and the installation, all those type of costs are now more important than the cost of the silicon wafers in the total cost of delivered electricity. So the main thing that you need for a competing technology is efficiency. So you need to have, I believe, a technology that's more efficient than silicon to displace it. So thinking in terms of a low efficiency, low cost technology, I don't think will be very profitable for at least for large scale power installation. Perhaps for consumer products and things like that, it'll be a different story. So silicon is already cheap enough. The real pressure is to improve the efficiency of the module so that you can leverage some of those other costs I mentioned, like transport costs. The fewer modules you have to transport, the lower they'll be. And so efficiency plays a big role in reducing a lot of those less glamorous costs that are now dominating the total electricity supply costs from solar. So thanks for the question.
Yeah, and actually a follow-up question from Paul Berger. So first of all, he thanks you for the great talk, and then he asks, do you see any future competitiveness for technologies like CIGS, cadmium telluride, and 3-5 tandems for terrestrial applications?
Maybe not for those specific technologies like 3-5s and SIGs, for example, involve elements that are either toxic like selenium or scarce like indium, so that you just couldn't do the volumes. Like last year's 140 gigawatts. I calculated with SIGs you could do about 30 gigawatt a year would be the maximum. So you're looking at a small market share for some of these technologies, and even cadmium telluride that presently has about 4 or 5% of the market. 30 gigawatts is probably the limit of what you can do there due to the tellurium issue. Supply of tellurium would be an issue. So you really need a material that's very abundant. You've got to be mining it, and at least 10,000 tons a year sort of quantity, because that's the amount you're going to need for photovoltaics, even if you're using the material as thin films. So you need materials that are already mined in, hundreds of thousands of tons a year, I think, if you're going to be able to obtain them cheaply and use them in photovoltaics. So, so a lot of those technologies are ruled out. But there is a role for non-silicon technology in this stack cell concept, because you need something other than silicon to stack onto silicon that has a different band gap from silicon at least. So we explored all silicon approaches using quantum dots and things like that to expand the band gap, but it wasn't very productive. So I think you're going to have to find another compound semiconductor that has the attributes of silicon, higher band gap, and abundant, non-toxic, stable and efficient materials. So that's the big challenge facing photovoltaics, because there are many contenders out there, but none of them tick all those 4 boxes. Thanks for the question.
And I think we'll take 2 more questions before we conclude. So there's a question from Zamir. Do you think that there is a role for thinner wafers, like below 100 micron silicon wafers for PERC cells in the near future?
Yes, definitely. Going to thinner wafers will help reduce the costs of photovoltaics. And some of the technologies I mentioned, like the heterojunction technology, which is one of the PERC competitors at the moment, is a very symmetrical structure. So it's a very low stress structure. So you can use that with PERC. It's a bifacial structure as well. So if you use that in glass modules, you have a very symmetrical structure right through, and that minimizes the stress within the cell. So so going to thin wafers make sense for that technology specifically. And it's probably necessary to bring the costs into the regime where it is competitive with PERC technology. So I think we'll see pioneering of thinner wafers, particularly for the heterojunction type cell technologies. And I think they're already talking about 130 type microns. And the IBC, the interdigitated back contact technology, is already using wafers around 130 microns. So there's already thinner wafers being used in the industry, but not for the mainstream. So it turns out that the wafer cost isn't the most important issue, and it's better to remove the extra challenges associated with thinner wafers in terms of increased breakage rates and things like that. It's better not to have to solve those. It's better to pay the extra for a slightly thicker wafer than to have to address lower yields from the thinner wafers that you'd see as a consequence. So yeah, I think the industry will steadily move to thinner wafers, although at the moment it's not a #1 priority.
Yeah. And then the final question from Ethan, he's wondering, for these bifacial modules, is there any different optimization for the support structure, because you don't want to shade the back of the panel?
Yes, that's entirely correct. So generally the strongest way of mounting a panel is to have the support structures going across the panel. How can I describe this? The panel is a elongated rectangle, and you have the cross members along going across the long side of the panels. And that gives you the highest strength. But for a bifacial panel, you generally have the support structures running along the long frame direction of the panel, so that you have nothing running across the rear of the panel. So that you use a different mounting structure, which is not quite as good in terms of the loads that the panel can withstand. So panels are rated generally for wind loading as well as snow loading. So they're the two big mechanical loads that the panel sees. But they're plenty strong enough for most environments, even with a non-optimal mounting structure. But yeah, so generally for a bifacial module, you'll have the support structures running along the long side of the frames. Is the most common approach, with nothing running across the rear, because as the questioner mentioned, you would be shading some of the rear with that and affecting the overall output. So thanks again for that question and the others that have asked questions. Thank you.
Okay, thank you. Lastly, I want to, of course, thank Martin for the excellent talk. So very good overview of what's happening in this exciting field. It's very big now, and there's a lot of developments. And it was also good to hear at the end that there's still a lot of unanswered questions that we as scientists can work on to solve it, from material science and other aspects as well. So thank you again, Martin, for the excellent talk.
Thanks, Bram.
And
thanks, Martin, and thanks everyone who joined today. Fantastic event. Thank you.
Okay, thank you.
Bye, everyone.
Bye.